Hi, my name is Max Ehrlich, and I'm going to be talking about the compressed video quality enhancement work that I did together with my colleagues at NVIDIA and my friends at the University of Maryland Department of Computer Science. So we call our system Metabit, and you can see an example of Metabit in action here on the right, where the blue boxes show the restored versions of each frame. This was a very practically minded project, and when we look at deep learning for video compression, we can see that there's been a lot of progress in recent years. A canonical example is ELF VC from Wave 1, and for the most part, it can match AV1 in terms of rate distortion, but it's significantly slower, and that's including a GPU, which is not necessary for classical video decoding. So it's not going to be competitive or consumer ready anytime soon. And the question we had was, how can we get deep learning into video compression sooner? And we're proposing to keep classical codecs like H.264, which covers something like 90% of internet videos. And as an example of how ubiquitous H.264 has become, this is the mandatory format for all videos for WAC-V, and in fact for all IEEE conferences going back for a few years now. The idea would be that we use a deep learning network to restore the degraded video, which was degraded by compression. And there's some big advantages to this because people without GPUs can still view the resulting stream since it's just H.264. The encode time would be very fast because there's no deep learning required for encoding. Decode time is faster than many deep learning codecs, and we could make it real time if we worked on the system a little more. And rate distortion is also better than many DL codecs and could be even better with more training. So as you could imagine, the idea of using a deep network to restore compressed video frames is not exactly a new idea, but there's a few problems with the way prior work was approaching it. And the one problem was the prior work was treating this as sort of a multi-frame image-to-image regression problem. In other words, they would take a sliding window of 7 frames and produce a single frame as output, and that's quite slow. If you're familiar with other video tests like video super resolution, one thing that can help is to align the feature maps from nearby frames. And this is often done with something like optical flow or deformable convolutions. One kind of unique idea that came out of the prior works is peak quality frames. The idea is that there's some frames stored in higher quality, and we can use those to help restore lower quality nearby frames. The problem is that prior works solved this by training yet another deep learning model, which would scan the video for these frames and pull them out, and that's quite slow. And finally, these prior works were all benchmarked on HEVC constant QP. We'll talk about constant QP a little bit in a minute, but this is essentially unheard of for real videos, and even worse, they were training one network per QP setting, of which there are 51. So we have to understand a little bit about how video compression works in order to understand our solution. The idea is that you have an entropy reduction in space, just like JPEG, and in time. And iframes are basically your JPEG images. They're called intraframes because they can be decoded with no external information. The P frames, or predicted frames, require at least one prior frame to decode. And when we're looking at iframes, the main thing we're looking at is this QP, or quantization parameter, which determines how much to round the coefficients, just like JPEG quality. The problem is you rarely interact with this directly. Usually you do what's called a constant rate factor. This allows the QP to vary over space and time based on the content of the video. So the P frames are a bit more complicated. They contain motion vectors, which is basically a block-based heuristic motion, and error residuals, which is everything that can't be modeled just using the block-based motion. So we can use all this to build a better restoration algorithm. First off, we don't need to compute optical flow because we can use the motion vectors, just reading them out to align the nearby frames, and it turns out that's good enough. We don't need to search for PQFs. It turns out that that's what the iframes are. They are the PQFs. That's what the prior models were detecting. The codec stores per block QP, so we can condition our model on this side information in order to adapt to the differing compression levels. And this is what allows us to use H.264 CRF, constant rate factor, which is extremely common in real life. So this is what our network does. It reads the motion vectors to align the feature maps. It reads the IMP frame structure to restore blocks of frames. It uses iframes to restore p-frames, and it uses the QP map to allow the single network to handle videos of different compression levels. And since we saved a lot of parameters by doing all this, we can reinvest those into the restoration network, and then we also do some things with the loss functions to help. Okay, so this is the overall network architecture. I've split this up into two phases, but it's one network trained end to end. So the first step is to do a really good job on the iframe, and we do this with by passing the iframe through a set of residual blocks, and then passing the pre-frames through their own residual blocks, which then give feature maps which we align and concatenate to make the iframe representation. We then generate the iframe from this. Then we use that high quality iframe, and we use the same motion vectors to back warp it onto each of the low quality P frames, and then we concatenate that together and generate the P frames. So this is our residual block, which is where we incorporate the QP map using spatial attention. We also do channel attention directly on the input features, so we find the best channel to use. And then we also add some loss functions, and I won't go into too much detail in the interest of time, but the idea is that since compression is specifically targeting high frequency details, we can use a difference of Gaussian scale space to reweight the frequency bands of the image and force the network to give equal consideration to high frequencies and low frequencies in its restoration. So we also add Wasserstein-Gann loss with a temporal consistency component and a texture restoring loss, which was from JPEG artifact correction. So how does this do? There's more comparisons in the paper, but to keep things simple, this is one recent model that we compare to. And the interesting thing about this is that that model with the blue and red bars is training a different model per CRF setting here, whereas ours is just a single model for all CRFs, and we're still able to outperform them by quite a bit. And now we'll go and look at some qualitative results. Interesting things to note here is the texture on the trees on the top and the sharpness of the lines top and bottom. And again, we have some much sharper lines here and some definition and detail added to the hands and arms. And then again, more texture on the leaves of the trees and of the roof, and detail and texture and sharpness added to the back of her dress. So in conclusion, we developed this compressed video restoration network, and we showed that by using knowledge of video compression, we can actually improve the restoration quality, which can give benefits over both classical and deep learning based compression. And this could be ready for use in near term. So please reach out if you have any questions. Thank you.